This is what most drum sequencers look like, packed with buttons and LEDs, all driven by a microcontroller. I want to design my own, but wiring up this many buttons on a breadboard, that would get messy quick, and we haven't even started coding yet. So let's take a step back. What if I don't follow that blueprint at all? What if I start from scratch and only add what I really need? That's the challenge for this video. What's the most minimal drum sequencer I can come up with without compromising on playability? But before we start patching things together, let's talk about what a drum beat actually is. If I tap something like this, what makes it a beat exactly? Two things. First, it's repetitive. And second, it follows a timing grid. There's an underlying pulse, a clock, and each tap either lands on a clock pulse or it doesn't happen at all. See these empty spots in our pattern? That's what we call rests. Okay, now how do we translate this to the world of electronics? Well, if you squint, it's really just a stream of binary data, hit or rest, high or low voltage. And the clock is just a voltage flipping between high and low at regular intervals. The shorter those intervals, the faster the tempo. Conveniently, we can get a clock signal like that from any basic square wave oscillator. So I'll grab one from my modular and connect it to Labor, a prototyping tool I designed specifically for developing analog synth circuits. If you want to build along, you can get your own in the Synths webshop. There's a link in the description. Okay, I've wired the clock up to this LED. Now, what about the drum pattern? Well, the simplest way to generate one is probably just pressing a button. I can configure this one so that every press gives us a voltage pulse, which we can then use to trigger a drum module. Of course, playing our pattern manually is not quite what we're after. We want to design a circuit that plays this pattern for us. But that means we need some way to store it and play it back in a loop. Now, that might sound like a job for a microcontroller, but there's actually a much simpler type of chip that's perfect for this scenario, a shift register. Think of a shift register as a clocked chain of binary memory cells. On each clock pulse, it shifts its contents one step to the right, while grabbing a new bit from the input. Once a bit reaches the end of the chain, it drops off. But here's the trick. If we connect the last cell back to the input, that bit circles around instead, looping through the register indefinitely. Add a few more logic ones, and you've got a full drum pattern rotating through the chip. Okay, but how do we use this to trigger a drum sound? Easy. We just watch the very first cell. It goes high whenever a 1 swings by, essentially playing back what we tapped in. That's our trigger signal. To try and implement this, we'll use the CD4015, a dual 4-bit shift register. For the initial setup, we'll have to supply the chip with 12 volts and ground. Next, we'll turn it into one single 8-bit register by chaining the two 4-bit registers. For this, we simply connect the last output of register A to the data input of register B, and we'll tie both reset pins to ground to enable the registers. To visualize the chip's internal state, we'll set up 8 LEDs, one for each data cell. Then we'll apply our clock signal to the clock inputs and our button to the first register's data input. Small side note, the clock signal should stay within the chip's supply range. Negative voltages can damage it. To test our circuit in practice, I've already set it up on the breadboard. If I push this button now, we should see a bit travel through the chip and then drop off at the end. Great, so how do we make this loop now? Unfortunately, we can't just connect the last output to the data input like this. That's because both the output and the button are able to sync current, meaning that if either is high while the other is low, we create a short circuit. To avoid this, we'll set up 2 diodes. These will block any current from flowing in the wrong direction. And to make sure the voltage at the data input doesn't just float when both button and output are low, we'll add a 100K pull-down resistor. So if I now push the button, our bit should loop around. Perfect. Let's add a couple more. Next, I'll take the register's first output and connect it to a jack socket. From here, I can route it to one of my drum modules. Cool, this seems to work. Let's add a couple more bits to the sequence. Something's not quite right here. As soon as we have 2 bits right next to each other, we only get 1 drum hit, not 2. What's up with that? Well, the issue is that our drum module gets triggered when its input voltage goes from low to high. We call this a rising edge. Take a look at our first output LED. Every time it switches from off to on, we hear a drum sound. But if 2 high bits appear in a row, the LED never turns off in between, so there's no second rising edge. How do we fix this? Well, you might have noticed that while the output LED stays on, the clock LED still blinks. This means that if we found a way to pull our trigger output low whenever the clock is low, we should get 2 rising edges and 2 drum hits. Great, but how do we do that? It's actually pretty simple. All we need are 3 components: an op-amp, a 100K resistor, and a diode. Here's how it works. Whenever the clock is high, the diode blocks, and whatever voltage is present at the trigger output gets buffered by the op-amp unchanged. But when the clock is low and the trigger output is high, the diode conducts, pulling the voltage at the buffer's input low. As a result, the buffer's output drops as well, creating a clean rising edge on the next clock pulse. And yeah, this actually gives us 2 drum hits for 2 consecutive bits. Great. Now, what if we fill the entire register? Luckily, this works as well. But now we've got another issue. Since we can only add bits, there's no way to edit the sequence. We could always reboot to wipe it, but let's be honest, that's a little crude. Ideally, I'd want to remove bits the same way we add them, by pressing a button. Unfortunately, we can't selectively delete data once it's inside the register, but there is a workaround. We might not be able to remove a bit directly, but we can stop it from looping. Think of it like this. Every time a bit reaches the end of the register, we have a choice. Do we feed it back, or do we drop it? If we drop it, we're effectively deleting it from the sequence. So if we could momentarily break the feedback loop by pressing a button, we'd be set. Implementing this isn't straightforward though, because most push buttons are normally open. They only connect when pressed. So if we'd put one into the feedback loop, the connection would be broken by default, and the sequence wouldn't loop unless we held the button down the entire time. To work around this, we'll use a PNP transistor. If we place it in the feedback loop like this, it conducts by default, unless its base gets pushed high by the button, in which case it blocks and breaks the loop. I've set up our clear button over here. Let's see if this works. Nice, it does. What's cool about this setup is that it lets you delete the step that's just about to play. It's like entering rests into the loop, the exact counterpart to adding triggers with the other button. Okay, so at this point, we've got a fully functional drum sequencer with an ultra minimal interface. Just 2 buttons. Well, almost ultra minimal. Currently, we're using 8 LEDs, 1 for each shift register output. That's great for debugging, but a bit overkill for regular usage. Since we're only using 1 output for triggers, we can simplify things. If we get rid of these LEDs and replace them with 1 LED at the trigger output, we should still get enough visual feedback, without all the extra wiring, clutter, and power draw. Speaking of power draw, to avoid overloading the op-amp's output stage in the long run, we'll drive the LED through an NPN transistor. Let's see if this is still playable. Turns out it's a bit tricky, because the clock LED is blinking really fast. 1 flash per 16th note. If you've used a metronome before, you'll know they usually tick in quarter notes, not 16th notes. It's just a more natural pace to lock into. So let's try slowing our clock LED down to quarter notes as well. For this, we'll use a simple binary counter chip, the CD4520. This chip actually combines 2 4-bit counters into one package. To start, we'll need to supply it with 12 volts and ground. Next, we pick one of the counters we want to use and activate it by pulling its reset input low and its enable input high. Now, when we feed it our 16th note clock, the chip begins counting pulses in binary. This means that the Q0 output toggles at half the input speed, giving us 8th notes. Q1 is half again, giving us quarter notes, and so on. For now, we'll grab the quarter note pulse from Q1, buffer it with an NPN transistor, and use that to drive our clock LED. Finally, we'll disable the second counter by pulling its clock input low, so it stays inactive. Here's how this looks in practice. Our LED blinks noticeably slower. Let's see if that makes tapping in a rhythm feel more natural. Yeah, way easier to lock into the groove like that. And if you want, you can even send that quarter note signal to another sound source, like a hi-hat or a click module, for an audible metronome. At this point, our sequencer is pretty fun to play, but it still sounds kind of flat. That's because every drum hit is identical, same volume, same intensity. To fix this, most sequencers allow you to program accents, louder hits that give the pattern some dynamic variation. Here's how it works. Drum circuits usually have both a trigger input and an accent input. The trigger tells the module when to play a sound, but the accent input controls the sound's volume. The higher the voltage, the louder the sound. So in addition to our digital trigger sequence, we'll also need an analog accent sequence. The orthodox approach would be to generate one accent level per trigger. Doing that would add a lot of complexity to our circuit though. So instead, let's see if we can cheat a little and still get something that sounds great. Rather than generating accent levels per step, we'll just use a slow triangle wave. At first glance, this probably looks wrong. The voltage is always changing and doesn't stay fixed from one trigger to the next. Here's the trick though. Most drum circuits don't track the accent voltage continuously. They just sample it the moment the trigger hits. So the triangle wave's position at that instant becomes the accent level. Okay, to generate a triangle wave, we'll set up a simple oscillator. I've explained how this topology works in detail in my FM drum video, but here's a quick recap. The circuit combines two building blocks, a Schmidt trigger and an integrator, connected in a feedback loop. On power up, the Schmidt trigger latches either into its low or its high state. Let's assume it starts high. This pushes current through the integrator's input resistance and into the capacitor. The integrator op-amp is wired to neutralize any voltage change at its inverting input, so it counteracts by pulling current out of the other side of the capacitor. This results in a downward voltage ramp at its output. Next, when the output has dropped far enough, the Schmidt trigger flips to its low state. Now current flows the other way, causing the integrator's output to rise. Eventually, that output climbs high enough to trigger another flip, and the cycle repeats. Here's how this works out in practice. I've connected my scope to the integrator's output. As expected, we get a slow triangle wave. Next, I'll patch it to the drum module's accent input. That's not what we expected. Instead of just going quiet, the hi-hat cuts out completely for part of the cycle. What's up with that? Well, it turns out the module doesn't produce any sound for a negative accent voltage. To fix it, we'll need to lift the triangle above the 0 volts line. How do we do that? Easy. All we need is a simple clamping circuit. It works with any waveform, including our triangle wave, but it's easiest to explain using a square wave. So let's imagine we apply a ±5 volts square to the input. During the square's first low phase, current gets pulled out of the cap and flows into it on the other side. This will leave us with -5 volts on the left and about 0 volts on the right. Then, when the input swings high, the charge on the right is trapped, since the diode blocks current from flowing back to ground. So the voltage added on the left stacks on top of the 0 volts on the right, giving us a 10 volts output. And that's it. The signal is now oscillating above the 0 volts line. But there's a catch. We can't just use the signal directly, because pulling any current from the capacitor would mess with the clamping mechanism. So instead, we'll buffer the output using an emitter follower. That gives us a low impedance version of the lifted signal, without interfering with the circuit. Let's see if this fixes our issue. Yeah, our hi-hat does not cut out anymore. Instead, we get a wide range of dynamics, from barely audible to super loud. Let's see what happens if I adjust the LFO's frequency. This is pretty cool. While slow speeds give us gentle swells, faster ones create complex patterns that feel surprisingly deliberate. That said, the dynamic range might be a little too extreme in some scenarios. So let's add a modulation depth control that allows us to tame it.
To get there, we'll simply replace this resistor with a potentiometer. That way, the pot works double duty, acting as the emitter follower's load and attenuating the LFO at the same time. To keep the output impedance low, we'll buffer the result with yet another emitter follower. And why not throw in another LED for some visual feedback while we're at it? Here's how this works out in practice. As I turn the depth knob, you can hear the maximum accent level drop. At the lowest setting, the drum hits all come out at the same low-level intensity. Crank it up, and we're back to the full dynamic range.
But you might have noticed something curious in how the accent pattern behaves. It's like the accents are sliding in and out of sync with the pattern itself.
That's because our LFO is free running. It's not synchronized to the clock. So the triangle wave cycles independently, and the accents fall in different spots each time the pattern loops. This isn't a bug, though. It's what you'd call a polyrhythm. Two rhythms with different rates running side by side. This can sound surprisingly organic, especially in ambient or generative contexts. But sometimes you might want accents that line up with the beat predictably. How can we make that happen? One idea would be to carefully adjust the triangle's frequency so that the accent pattern repeats exactly once per loop. But in an analog circuit, that's easier said than done. Even tiny mismatches add up, and the two signals start drifting apart. So here's a better idea. What if we just forced the triangle to restart from 0 at the beginning of each loop? That would give us a perfectly repeating accent pattern, regardless of the triangle's base frequency. No drifting, no fine-tuning required. And while that might sound tricky to pull off, the actual solution is surprisingly simple. Here's the idea. Our triangle wave is generated by charging and discharging this capacitor. So the exact position in the wave cycle, whether we're on the way up or the way down, depends on how charge is distributed across the cap. If we suddenly even it out, the oscillation should snap back to its starting point. Okay, but how do we do that? Easy. We just need to bridge the capacitor with a resistor and an NPN transistor. Then we apply a short voltage pulse to the big base resistor, which activates the bridge and allows the cap to quickly discharge. This resets the integrator's output to 0 volts. Once the voltage pulse disappears, the oscillation simply resumes from that point. Great, but where do we get this voltage pulse? Well, we said that we want to reset the triangle at the beginning of each pattern loop. Our pattern is currently 8 steps long. Conveniently, we already have a signal that jumps from low to high every 8 steps. The CD4520's half-note output. But there's a small catch. That output stays high for 4 steps, which is way too long for our purposes. We don't want the reset transistor to stay on. We just need a quick blip that discharges the capacitor and then gets out of the way. So before we can use it, we'll need to shape the chip's output into a short voltage spike by adding a small cap at the oscillator's reset input. The cap only lets a quick burst of current through, creating the short pulse we need. Okay, that was a long preamble. Let's see if this actually works as intended. Here's the original free-running version again, without sync. And here's what happens if I connect the 4520's half-note output to the new LFO reset input. We can even take this a step further. I'll set up a 3-way switch so we can either let the LFO run freely, sync it to the full pattern length, or sync it to half the pattern length for even straighter accents. Cool. The 3-way switch combined with the frequency knob gives us a huge range of possible accent patterns that sound deliberate, even though they're basically generated by the circuit itself.
At this point, we've built a feature-complete single-channel sequencer. But of course, a drum beat isn't just one sound.
Even the most basic beats combine multiple voices, like a kick and hi-hat playing side by side. So realistically, one channel just isn't enough. Thankfully, our design is so minimal and so modular that we can simply clone the sections we need. To get a second trigger pattern, we'll simply double the 4015 based tap looper. And for an additional accent sequence, we'll set up another synced LFO. There's just one small and slightly silly problem. I don't have a second breadboard-friendly push button for clearing steps, but maybe that's a good thing. It gives us an excuse to simplify the interface even more. Here's the idea. What if we could use the same button we tap to add steps to remove them as well? All we'd need is a global modifier button that, when held down, turns every trigger into a clear button. That way, we could drop one button per channel without losing any functionality. To recap, right now, pressing the per channel clear button disables the PNP transistor in the feedback loop, which stops bits from looping back to the data input. What we want now is to trigger that same behavior, but only when both a new global clear mode button and the channel's trigger button are pressed together. To pull that off, we'll add an NPN transistor wired like this. When both buttons are pressed, that transistor turns on, allowing current to flow. This raises the PNP's base voltage, which turns it off, and breaks the feedback loop. But if either button is inactive, the NPN stays off and the loop continues. Okay, I've added that NPN to both tap loopers. If we got everything right, pressing this button together with the trigger should now delete steps. Weird, nothing happens. What's up with that? Well, the problem is, even though we break the feedback loop, we're still pulling the data input high. So we end up writing a new step while trying to delete one, which cancels it out. To fix this, we'll add another PNP transistor between the trigger and the data input, controlled by the clear mode button. It works like this. When clear mode is off, the PNP conducts and trigger presses behave normally. But when clear mode is on, the PNP shuts off, cutting the connection and preventing new steps from being added. Now, the trigger button should write steps or delete them, but never both at once. At least in theory. Let's see if this actually works. Great, it does. So now we have two voices, full control over each pattern, plus dynamic accents, all with just 3 buttons total. Not bad.
But here's the exciting part. We're only just starting to squeeze real mileage out of this thing. With just a few small tweaks, we can push it even further.
First up, sequence length. Earlier we saw how a free-running LFO could create polyrhythmic accents, but that was modulation on top of a sequence. What if we could get that same type of evolving movement between our two patterns? Right now, they both loop after 8 steps, so they always line up the same way. But if one looped, say, every 6 steps instead, we'd get a 3/4 polyrhythm, which should create some interesting rhythmic tension. Okay, so how do we shorten the pattern? Simple, by shortening the feedback loop. Right now, we're routing the shift register's 4B output back to the data input, which gives us an 8-step cycle. If we move that connection to the 2B output instead, we're down to a 6-step cycle. But why stop there? If we add a 3-way switch to select the feedback tap point, we can toggle between multiple loop lengths on the fly. For example, 4B gives us 8 steps, 2B gives us 6, and 1B gives us just 5, for an even more off-kilter feel. To test this, I've added loop length switches to both channels. Let's see what happens when we set one to 8 steps and the other to 6. That gives us a nice rolling groove. Now let's try something a bit more off balance. 8 and 5 with an unsynced accent sequence on top. It's kind of wild how much variation we get just by changing where the loop resets. And there's still more we can do without adding much complexity. So far, both channels have been ticking along to the same 16th note clock. But what if we slowed one of them down to 8th notes? That gives us the illusion of a longer pattern at the cost of resolution, a feel that's usually referred to as halftime. To make it happen, we'll add a simple 2-way switch at each tap looper's clock input. One side connects to the main 16th note clock. The other taps into the 8th note output from our clock divider. This lets us switch each channel into halftime mode independently. So what does that sound like? Let's combine different sequence lengths and speeds and see what kind of results we get.
With just 2 switches and a handful of wires, we've greatly expanded what our circuit can do. But just before we wrap this up, I have one more idea.
So far, we've used a triangle LFO for generating accents, but that's not our only option. We can also repurpose one channel's trigger pattern for this. That works and gives us full control over the accent pattern, but it's just binary, loud or quiet. Let's try turning that into something a bit more nuanced. Right now, we're only using a single output to drive accents. That output just flips between high and low, but the register holds more data, 8 bits moving through it in parallel. If we tap into multiple outputs at once, we can treat the combined signals as a binary number. With 4 outputs, we get 16 distinct values. Now here's the trick. We can convert each value into a corresponding analog voltage, and use that as our accent level. Instead of just on-off, we then get stepped intensity, soft hits, loud hits, and 14 steps in between. And the best part? We can do that conversion with just a couple of resistors. Here's how it works. We take 4 outputs from the shift register, let's say 1A through 4A, and run each through a resistor into the same point, like a simple passive mixer. But instead of using identical resistors, we'll pick values that roughly double from one to the next. This way, each output has double the weight of the one preceding it, just like bits in a binary number. This gives us 16 distinct voltage levels between 0 and 12 volts, all evenly spaced. Since modulation signals normally stay below 8 volts, we'll scale this down using a 15K resistor to ground. And to keep the output impedance low, we'll finish it off with a simple emitter follower. On the scope, you can already see the voltage jumping between different levels. Let's patch this into the accent input and hear how it sounds. Instead of just loud or quiet, we now get a range of accent levels. The pattern we tapped in is still doing the heavy lifting, but it's padded with little ghost notes. And if we tap into different shift register outputs, we can even move those ghost notes around. And the best part? We're not limited to accents. Since this voltage jumps to a new fixed level on every clock pulse, we can also use it to control pitch, something that doesn't work with our LFO since its output is always drifting.
You don't have precise control over the notes, but that's kind of the point. It's fast and messy in a good way. Perfect for generating raw, rhythm-driven melodies with almost no effort.
At this point, we've designed a drum sequencer that's extremely minimal, but surprisingly capable. It supports full pattern programming, 2 types of accents, pitch modulation, and per-channel control over loop lengths and timing. And all of it runs on just 2 logic chips with no code at all. That said, our breadboard setup is fiddly and takes up a ton of space. Definitely not something I'd want to perform with. So to turn this from a test bench experiment into a real instrument, I hit up my friends at Erica Synths and asked if they'd help develop it into a full Eurorack module. Here's what we landed on. A 4-channel version with 16 instead of 8 steps each, paired with a built-in clock generator. We also settled on 2 LFOs, since most grooves only need accents on 1 or 2 voices anyway. A couple weeks later, this showed up in the mail. Time to heat up the soldering iron. Putting this together felt kind of surreal. A few weeks ago, it was just an idea on a sketchpad. Now it's a real module. So how does it hold up musically? Let's try a few different styles and see where it shines.
Turns out we were able to take this minimalist idea pretty far. Further than I expected, honestly.
So we decided to add it to the series of DIY percussion kits I've been developing together with Erica since.
That way, you can breadboard along with this video and build the final module yourself. You can grab it from the Erica Synths webshop. And if you want to dive deeper into circuit design, check out my Patreon.
There, you'll find bonus content like circuit design essays, challenges, scrapped video scripts, and regular project updates. Anyway, thanks for watching, and until next time. See ya!